Gil is presenting tomorrow at Yale, and today he was doing an 8-hour workshop. He arrived in Melbourne yesterday morning, a little bit jet lagged, so it's pretty awesome for one that he's actually agreed here to come and present at the meetup. He's on the JCP, so the Java community process, which is kind of important because he helps shape which way Java goes through JSRs and some other fantastic stuff. And I also hear that you also help out on the legal side of things as well, so, which is kind of also very important for any kind of open source community project. And so, yeah, we're really lucky to have Gil talk about faster Java objects. I'm going to let him do all the explaining on that, but please give me a hand in welcoming Gil to Mob JVM.
Thank you. So if my voice gives out in the middle, I apologize ahead of time. I didn't realize quite what I was signing up to do with. You know, flight in yesterday, jet lag night, 8 hours of talking, and this is my evening. The subject I've been talking about both at a workshop and at Yale tomorrow is actually about latency, understanding, measuring latency, all sorts of mistakes people do there. This is not that. This is about speed, not about measurement. And this really represents an effort that Martin Thompson and I started a year and some ago. It started from an argument. That's always the best way to start work. You say, I think this, let's code it and see what happens, right? And I mean, FAST Java object, faster object arrays is basically about trying to close what we think is the last remaining gap in speed between Java and C-style languages. And when I mean the last remaining gap, I'm not talking about missing optimizations or syntax. I'm talking about inherent inability to do speed. And we think that the only thing left is memory layout. That's the only thing where Java is actually behind. We'll go through what and why as we go through there. There is actual working code at ObjectLayout.org. It's all on GitHub. It's all public domain code. So you can look at it and not worry about being contaminated. And you don't have to do anything specific with it. You can keep it open, not keep it open. Just don't blame us for it. And the overall concept here is, you'll see in the code, if you look at it, it's vanilla Java code that works on any JDK today, but it's aimed at going faster on JDKs that could optimize it in the future. So I'm going to start by saying what object layout is and isn't. So the focus for object layout is to match the raw speed benefits that we get in the C family of languages from memory layout artifacts. And I'll get to be specific about what I mean by that, so I know that sounds a little fuzzy right now. What is it about within the Java scope? We're talking about regular idiomatic Java plain objects. This is not about coming up with some new type. This is not about coming up with some new syntax. In fact, this will run on Java 6. We're going, we don't need Java 8 or 9 or 10 for this. The code will run as is on Java 6. We're capturing semantics and making it possible to make the semantics go fast if we can optimize those semantics under the hood. The focus is on three things. It's on speed. Speed, right? It's on plain Java objects, nothing other than Java objects. And it's on the heap. I don't care about off-heap stuff. That's for other people to deal with. So this is not about any of these things. We're not trying to improve footprint. We're trying to not trying to save anybody's space. We're not trying to reduce any kind of overhead. If it doesn't make it go faster, I'm not interested in it. I'm not looking to compress anything. Memory is cheap. If you know what I do for a living, you know I think memory is really cheap. And you know I think garbage collection is a non-existent problem because we've solved it. At some point, other people will too. It's not about off-heap solutions. Nothing wrong with off-heap solutions. They have their place, especially when you communicate with things that are outside of JVM. But this is not about off-heap anything. It's about regular Java objects on the heap. It's about speed. And this is not about immutability. Nothing wrong with immutability, but nothing wrong with non-immutability either. Things that want to deal with new types that are immutable, and whether they're functional or value types, there's a good place for that. This isn't that place. So all of these are not right or wrong, they're just orthogonal to what we do. We just don't care. This is about speed for regular Java objects on the heap, and only that. So there are two things that usually people come up with when I talk about this. After I've said this is only this, they immediately say, so is this like value types? And is this like packed objects? Why? Because I just explained that it's not, so they have to ask. So how is it not? Well, there's no relationship between this and value types, no contradiction and no tightness. There's no relation to Java packed objects, which is an IBM project that is very interesting for describing structures off the heap and some on the heap. And also not related to similar efforts around JNR or FFI, if you know what those are, which deal with APIs to native libraries, ways of automatically marshalling parameters to C structures, things of that type. Those are fine efforts. We don't care about them. It's laser focused on the problem I talked about, which is speed for regular Java objects on the heap, and none of these address any of that. Value types are not about speed for regular Java objects on the heap. Packed objects are not about speed for regular Java objects on the heap. It doesn't conflict, it doesn't contradict, it doesn't have real overlap. There is a tiny bit of overlap, but when I say there's a tiny bit of overlap, it's the same kind of overlap that array lists and hash maps have. They're both bags you can put objects in, but they both have a place in the world. One last picture on how they're not the same, and then we'll move on to what it really is. Value types, object layout, and packed objects have a little bit of overlap. Value types, which are a really cool, sexy feature that I really wished made it into Java 9, probably won't be there, probably be Java 10. How many of you know what value types are? Show of hands. Okay, so value types are focused on things that kind of, the mantra there is they code like a class but act like a struct, like a value. How many times have you had to return something from a method and you were annoyed at the fact that you can only return one thing from a method and that you have to allocate an object to put two things in? And value types are there to solve that. How many times have you had the problem in reverse where you're passing something into a method and you need to pass two things? It's the same. Value types are a great way to structure things both in and out as parameters on the stack. So on the stack is very important. They're great features for compilers to optimize these things so you don't allocate on the heap and you can analyze things away. Return values parameters, they are immutable. They are values, just like an integer is a value. But it can have many things in it. It's really cool. And there's a lot written about this. When this comes, it'll be a major language feature change. There'll be new syntax. There'll be new things that Java C compilers do. The IDs will do new things. All kinds of stuff will happen. And then we will get really cool features. Packed objects are about communicating precise layout with things that are not Java. For example, if you're going to talk about network packets, the TCP IP header has 40 bytes in it, and they have to have specific values at specific places. You don't have the ability to say, let Java figure out where to put them, because there's a right way and a wrong way. So you need to describe them. Certainly when you communicate with native libraries and you're passing a parameter like a time val structure, again, that has a structure, a layout. You have to describe it. Packed objects, JNR, and FFI all deal with that, and they all deal with it mostly for off-heap behavior, mostly for sharing data with things that are not Java. In contrast, object layout is about speed for Java objects on the heap, right? You can think about it this way. There'll be new code for value types. When you use value types, you will write code that will not work on any current JVM and will be new. And only new code that can handle that will be able to deal with it. There'll be new code for packed objects. Code, depending on what people choose, this might not even be an object. It may be a new type, a root type. For object layout, Objects are usable with all existing code. These are regular Java objects. They're all derived from object. They can do anything an object does. And you can put objects in, send them around. All existing libraries can handle the content of these things. We have full compatibility with the millions and millions of things that people do. The overlap is over here. In all three things, I can make an array of small footprint things. Whether they're an array of points that have x, y that are mutable, immutable, or other things. You could probably express them in all ways, but that's not the key example. So where did this come from? It started with an argument. Martin Thompson and I were basically arguing, and one side of the argument looks like this. We need structs in Java. C-style structs, things that let us control the layout, things that are not full-blown objects, things that can sit in arrays so we can walk over them. And the best evidence of that is take a look at what the high-performance code in Java looks like and see what people that do it end up doing. Whether it's low-latency trading or messaging and off-heap structures, whether it's netty and other things, people end up doing interesting, weird things with byte buffers, byte arrays, flyweight objects, scrolling over them. There are things that are clearly being done because of the lack in Java around speed and structure. The counter-argument was, we don't need structs, we already have structs. They're called objects. They're perfectly fine. What we're missing is semantics that tell us, that capture the thing that allows us to go fast. Why is it that Java objects can't go fast, and what is it fundamental about the structs that makes them able to go faster? And we focused on that and looked for what I call the enabling semantic limitations. Going faster is not about adding features, it's about taking them away. It's about saying there are certain things this cannot do. Because it cannot do them, we can optimize it. We can lay out in a certain way. So let's take a look at where the speed we're seeking comes from. Where does C get its speed with memory layout? There are two primary things that happen in common C layout structures. One of them is what we call dead reckoning. Dead reckoning is the ability to get to a field of data without following pointers to get there. For example, if I have an array of 100 structs, and I want to get to struct number 17, field 3, from an array. In C, I'll take the pointer to the array, I'll add 17 times struct size, add the offset to field 3, and I have an address. I didn't access memory yet. I just took a pointer and did some math, and I have a pointer to the field I want, and I just access that and get it. We call that dead reckoning because we don't have to follow pointers. We dead reckon directly to the spot. Eliminating data-dependent loads gives you speed. Data-dependent loads are terrible things for CPUs to do because you don't know where the next thing is until you get the next thing and the next thing. So it's not just cache misses, it's also the pipeline even knowing where to go. Data-dependent loads are probably the hardest thing for a CPU to blow by. So dead reckoning gives us speed. If we can compute the address of something we need to access without going through additional data dereferences. The other part we get speed from is streaming. Streaming comes from being able to move data in and out of the cache fast, and doing it because we know exactly what the stride or pattern of access is. So if we go down an array of a lot of structures and we access field number 3 in each and every structure, they are equal in distance in memory because they're all the same, then whether it's software prefetchers or more importantly the current hardware prefetchers, the hardware will recognize the stride while moving it. It can actually follow 4 or 6 of these streams at the same time. It'll say, wait a minute, he's accessing here, and then here plus 34, and here plus 34, I guess the next one are coming at that stride. And it will actually go and prefetch for that. And when it prefetches for that, we get to not take latency hits. We replace a latency problem with a bandwidth problem. So rather than every access that is not currently in the cache, waiting until we get it from memory, the hardware went and brought it before we even needed it. And now we're just limited by how fast the hardware can bring things in. And the hardware can bring things in fast. I mean like 60 gigabytes a second fast, not slow. So we get to eliminate latency by streaming. This is why laying out memory in equidistance things is very important for access that is not random. So these are the two basic speed enablers we're looking to have. And when we look at limitations and what enables these, we can look at a basic difference between two arrays. We have the object array in Java, the array of objects, and we have the array of structs in C. And what I'm saying is that the array of structs in C is inherently faster than the array of objects in Java. Inherently meaning there is no way to build an optimizing layout that is valid in Java that will match this speed. Why is that? It's because the semantics are different. The Java object array is a mutable array of objects that have the same base type. It's an array of things that are object or subclasses of them. It could be an array of things that are foo or subclasses of foo. I can replace element number 7 in an array. It could be one element now and it could be another element later. That's the mutable part. So that's the quality of an array of objects in Java. That's the semantics. It's mutable and it's same base type. In C, we have an immutable array of exact same type. It's immutable because struct number 7 in the array is struct number 7 in the array. I can replace anything I want inside of it, but I cannot change which struct is struct number 7. There is no put operation in an array of structs. There's a get operation, and you can write any field you want in there. It's exact same type, meaning it's exact same size. There are no subclasses. Every element is exactly the same size. And those two qualities together are what makes both dead reckoning and streaming possible. Or more importantly, mutability and non-uniform member size each independently break those two qualities. Why do they break them? Well, if I have a mutable array and I can replace what element number 7 in the array is and point it to some other new place, there's by definition no way for me to compute what the address of that place is from the array address. It can be replaced later, so I have to look it up. I have to look up a pointer and I have to pointer it to follow it because who knows where it's pointing? Right? It has nothing to do with what the structure of the array is. Somebody put it there. Similarly, if you have mutability, because the object is somewhere else, there is no streaming, right? There's no constant stride. Now, if I'm walking down this thing, element number 7 is over there. It's not laid down in memory and so stream. That's the mutability part, ruins both. The non-uniform object size separately and independently also ruins both. So if each object could be a different size, then how do I compute the address of element 17? I need to know the length of each element until element 17 to figure this out. There is no way for me to say this plus some size times 17. But there's no way to compute the address. There's no way to dead reckon if the stride isn't equal. Similarly, if the stride isn't equal, there is no stride, right? I don't get the streaming. So both of these separately, both of the key qualities of the object array in Java ruin Java's ability to do anything with speed and layout. We have to follow a pointer. We can't pre-compute it, and we don't get to stream through memory. In object layout, we have a new type. This is not some new language type. This is just a class. You could write it yourself. It's called a structured array. It's a generic collection of objects, and it has the qualities, the semantic qualities of an array of structs. It's not an array of structs, it's an array of objects, but it's immutable, and it's of exactly the same type. You cannot put subtypes in there. That's the contract. That's what this class would do. That's its definition. It supports a get, and it doesn't have a put. When you make the array, all the content is there. All the content is of the type you set. That's exactly what happens when you make an array of structs in C. And that's the secret to speed. It's not about the language, and it's not about other tricks. It's the fact that the semantics allow us to lay it out flat in memory. We took away the things that disallowed it. So that's an example of identifying what the semantics are and then choosing them carefully. Now, the target forms for object layout are the common C-style constructs for memory, an array of structs. That is the equivalent, we use the equivalent of that in a structured array. The second one is what we call a struct inside a struct. One flat structure inside another flat structure. This is the C syntax for declaring it. And when you have the syntax, you could go into bar, you can derive the address of bar from foo. That is dead reckoning again. And if I have an array of these foos with bars inside, I can stream to bars. The third form that is very commonly used is a struct with an array at the end. This is commonly used for messages and packets and buffers. There's some sort of a header or an envelope, and at the end of it, there's a dangling array of bytes or array of longs, and that is a variable size. Variable meaning not you can grow and shrink it, but each instance could have a different length of that array. Right? Packet A could be of different length than packet B, but they're both packets. Now these three things are common structures. We don't really have to discuss their use cases because they're so prevalent you just have to go see some C code and look at how people use them. Each of those has the benefit of dead reckoning and or streaming. When you combine them together, you get a lot of both. Okay, so these are the main things we're trying to address, and none of these three things could today be expressed in Java in a way that will gain the speed. There is no way to express this concept in Java in a way that a JVM can optimize layout for. The reason is we don't have any Java classes with these semantics. And if we wrote them ourselves, there's no way for the JDK to know that that is the semantic. So we started off on this project, and the idea is to capture the semantics and enable speed, not by making it go fast, but by very carefully designing the API so that it would be possible and allowed to lay them out the right way. So that's capturing it. The theory is that we could do this without any language change, and we think we've shown that. And we want to capture this in a vanilla Java implementation that works today on any JVM, on any JDK. It doesn't go any faster. It doesn't go any slower. It just has these qualities. That's step one. Now once we have step one, we can have future JDKs recognize what this really is. Knowing that that's what the contract is, they can now optimize it. Rather than lay it out with an internal array of objects, they can lay it out as a flat array of structs or objects. Rather than have a struct and a struct actually have a reference to the other thing, we can actually lay them out together. That's a problem for the JVM and the JDK to solve in the future. The key thing is to capture the semantics that will enable that. And the only difference between what we call vanilla, which is run on any JDK, and intrinsified, which is an implementation that a JDK actually optimizes, the only difference between those two will be speed. There will be zero semantic difference. You won't be able to write one that will only work in one and not the other. Okay, that gives us compatibility. Now, we didn't come up with this concept, we copied it. This is how Java Util Concurrent brought itself to the world. How many of you remember the history of Java Util Concurrent? Anybody here old enough? Here. So Java Util Concurrent didn't start inside the JDK. It started as edu.unioswego. It was a Dudley private library that was built as public domain code. And it captures semantics that enabled concurrent operations. It was vanilla Java code. It could run on any JDK. It ran on JavaOne Rock. There were no language changes at all. To date, up to now, there is 0 language features that deal with concurrent libraries. We might get a few features in Java 9 around volatiles and atomics. But this has been in the JDK since Java 5, and there's still no language features. These are just libraries with known semantics. The implementation in vanilla worked. It could show itself, it could prove itself. People could play with it, they could kick it around, they could figure out that the API is wrong and fix it before it was standardized. That's a key maturation step. We expect to go through the same thing. And you could implement it in vanilla Java. You can implement an atomic long without an underlying CAS instruction. You could use a synchronized block. It will be really, really slow, but semantically it would have the same meaning. So it could run on anything. Then the JDKs recognize the semantics and optimize them. So instead of an atomic long being implemented as a lock, it is now a single concurrent swapping structure, instruction for doing the right things. That's an optimization of something that has exactly the same semantics, whether it's fast or slow. Now, a key part of enabling this is that the library got moved from being just some other people's library into the JDK. It became Java.util concurrent rather than what it was before. And moving it into the Java namespace meant that JDK could rely on that semantics not changing. Generally, it's more dangerous for a JDK to optimize something that's not part of the JDK. Because who knows, somebody might replace the class. Maybe they don't mean exactly this contract. When it's part of JDK, it's spec'd, it's standardized. We know exactly what it's supposed to do. The implementation doesn't matter. You can replace the implementation all you want as long as you don't change what it does. So I gave you a little bit of a feel for background. Let's zoom into one of these. By the way, if you guys have questions about what I said so far, feel free to interrupt. Kind of need that, want that. And this is a good spot to do it because we're going to zoom into structured array. So any questions so far? Run in the back.
So in fact, that's a good slide to start at because the question's actually on the third one. How does dead reckoning work on a struct with variable field length?
So let's talk about C. Ignore what we do right now in Java. The special thing about struct with array at the end is the array is at the end. It's the last thing in the array, in the structure. There is only one variable size thing. So all the fields have constant offset. Right? You take the struct, you add 16, you're at field A. The array has a constant offset to its base, and then you add the offset in there. That means you can dead reckon straight from the struct to any element in the array without an additional dereference. That's literally what happens when you define a struct and put a byte array at the end with no content, and later malloc more space than you need. That's how that works. You just need to make sure that there's nobody else back there and that's your memory. In Java, that's not quite how it's going to work, but technically that's what happens under the hood. It's just this block of memory, the beginning is known, the other one is, sometimes it's 1 kilobyte, sometimes it's 24 bytes, that depends on what you allocated for that instance. Does that answer the question?
Isn't that cyclical, like wherever the struct packet is allocated in memory, the director, whatever the string is, would be just next to it, from the memory layout point of view?
Are you
So
asking
how would
about
you
the implementation we might do for object layout, or about C?
About C.
So in C, C is pretty simple. You allocate the struct, a room for the struct, and you say the struct starts here. And all the struct is just known offsets from a pointer. And in reality, an object is no different than what you just described. That's exactly what an object is too, right? The field number 3 in the object is a constant offset from the beginning. When you have a subclass, what you're doing is actually adding fields at the end. So none of the base class offsets change when you have subclasses. That's why everything is fast to access anyway. The structs and objects are very similar in what actually happens in memory layout. The differences are that with structs you can do these things and you can't do any of them with objects today. We don't have a way to declare that. There are no variable size objects in Java except for the arrays, for the primitive arrays. And primitive arrays have very specific semantics. If they are references, they are mutable, same base type objects, which is not what we're looking for.
So how now, I don't really familiar with JVM, so how now it's storing arrays of objects? So to my mind, each object in Java is like a pointer in C. But if we have array of pointers, we know what's the length of each object in this array, and we can see through this array.
So each object reference in Java is like a pointer in C. An array of objects in Java is equivalent to an array of pointers to structs in C. Not an array of structs. It's an array of pointers that point to random structs. So there is an equivalent C structure that looks like an array of objects in Java. There is one, it's just an array of pointers. Nobody in their right mind uses an array of pointers to talk about things that they can say there's 100 and they're the same size. Right? You use it if you need mutability and you need different structs of different lengths. But you don't use it when you have...
Just have one piece of memory, yeah, that we can access fast. Yeah, okay.
Yeah. So, and in C you can express both. You can have either structure. In Java there is only one, the one with the pointers in the array that points somewhere else. Yeah.
When you add mutable object to that structured array, and then you change one of the fields using a setter
Yep.
in the original one, would that change also be reflected in that structured array?
So I get this question a lot. It starts with when you add a mutable object to the structured array, and that's where you have a problem, right? You cannot add anything to a structured array, right? And a structured array is immutable. You cannot put anything in it.
How do you add values?
You don't
Populate it.
add things to it. You get the objects in it and do whatever you want to the object, right? So you can get
Right.
element number 7, and you can change and mutate anything you want in it, but you're not replacing
I
who
see.
7 is.
Okay.
So you don't put, you don't add, you get. And then go mutate it, which is exactly what you do to an array of structs. Right? And that's really the key. I didn't mean to ding you on the question, it's just the answer is in the question, right? There is no put operation, there's no add operation. They're all there. When you made them, you said you want them there and they're not going away.
Just probably to continue this question on mutability, like in Java, like objects can contain other objects and be hierarchical structures. If you're going to mutate something inside, you should add some preventing freezing mechanism for those inside. Object will not be replaced with some descendant, because Java allowing you to do those extended base.
So we'll get into specifics here.
Yep.
For what I described in our structured array, I don't need any of that quality, because I have an object in there, and if that object has another flat object inside, it'll be flat, and if it has a reference to an object, it'll be a reference. It's whatever object you have. Arrays of structs, or structured arrays, in object layout can hold any constructible Java object. It can hold the objects you have today. It doesn't need to be special. They don't have to have any special qualities. If you can construct it, you can create an array of it. That's the key thing about it. Okay? And it's for any Java object. When I say construct, for example, if it comes from a factory, you can't have an array of it. Why? Because the array has them. It doesn't get them from someplace. Factories make things. Okay, let's look at structured array and zoom in a little. So a structured array semantically is really simple. It's just a collection of objects of the same type. Exact same type, no, not subtype. Exact same type. So all instances in the same instance of the array are of the same type. They're arranged as an array. Okay, it's a collection of objects, but it has an index, it has a get. Okay? You can get element number X. Notice I didn't say that they're laid out flat in memory. That's optional, that's implementation. We're talking semantics, right? So it has the feel of an array. The collection as a collection is immutable. There's no put, there's no replace, there's no add, there is only get. You instantiate it with a factory method. This is an example. I want a structured array of length 100 with this class in it. That's the element. 100 of that. That's how I say I want one. Now, it's actually pretty elaborate because you have to construct all the elements at instantiation time. There's no later chance to do that. And as a result, there's very elaborate support for construction. This is a trivial case. If you have a default constructor and you can just do that, then fine, you're done. But what if the object you want to put in, you want to make this array out of, has final fields? Final fields have to be initialized in the constructor. So we need to somehow tell it how to do that. If you look at the code, there's fairly elaborate ways of, and expanded ways to do that. There's the easy ones when you have default constructors. There's other easy ones where you say, oh, here's the constructor and arguments, just use that. That works when you want them all to be the same. But what if this class had a field that was called myIndex? And that field is final, and it's supposed to be initialized to my index in an array, so everyone is different. There's a way to do that too. You can actually provide what you call a constructor args provider in a lambda expression form, or since this is Java 6, an anonymous class functional interface that looks like a lambda expression but is coded flat. And you could say, you know, given this context and this index, I want these to be the parameters. That becomes your code. So you can pretty much construct it any way you want. There are examples in GitHub that you could look at doing it. So the trick here is we need to give very elaborate construction support, because the last point at which you can do things is during construction, instantiation. Okay? That's one key trick. Without this, it would be highly limiting. If we said you can only have objects that have default constructors, that would dramatically limit what we could make arrays out of. If we said that you can only have objects that don't have final fields, that would also limit it. We don't want to do that. We want any Java object. Okay. Another key trick was figuring out liveness. Now, this took us a while because we started off with the notion that it's an array of these things inside. And if you have a reference to the middle of the array, that usually means you want to keep the whole array alive. That's what every other implementation in the world that has this array of structs does. That's what C# would do, and some other things where if you can have an inner pointer to a field of an object or to a member of an array, that inner pointer keeps the thing you point to the middle of alive. And Java doesn't have this concept today. You can only refer to objects. You can't refer to the middle of an object. So there's never a question of referring to the middle of something, I'm keeping something bigger alive. This was an interesting challenge because, you know, we looked at how other arrays of structures are done in garbage collected environments and wanted to figure out how we teach a garbage collector to do this. And there's actually interesting material on how to do that. But it gets complicated and it's messy. It's not natural for the current JVMs to do it. And about a month into trying to figure out ways to do this, Michael Wolf, he's our chief GC guy. We built C4 together. He gets up and says, tell me again why we're trying to keep the array alive. And I didn't have a good answer. Because other people do that is not a good answer. So we kind of reversed this and said, why do other people keep the array alive? And we realized they keep the array alive because they don't have objects. They have structs, and structs don't have liveness. They're not first-class heap elements. They're inside something else, so the thing they're inside of needs to stay alive for the struct to be alive. But we are talking about regular objects. They're regular objects. They can be locked. They can have identity hashes. Whatever you can do to an object, and you can have a reference to it. And then everything fell into place. Structured array is not special. It's just a collection of objects. Do you have any other collections of objects that stay alive because one of the objects in them is alive? That just isn't idiomatic Java. You put something in a hash map, and that stays alive. That doesn't keep the hash map alive. The hash map keeps the thing alive. Now you can also put the same object in a hash map and an array list and in 15 other things. There's no contradiction there. So this is just a collection. We have real liveness. That means that it's just an idiomatic collection, and it keeps the members alive, and the members don't do anything implicit about that. And that means that we can actually have all the members participating in the object graph. I can take a structured array of elements, and I could take the elements and put them in a hash map to index the array. And I could run linked lists through them, and we could do both at the same time. There's no contradiction. Whatever you're used to doing with objects, you can do with this stuff. This is just a collection of them. Now, under the hood, you know, implementations that want to go fast will want to do things like keep the collection together. So if it's moving around, it'll want to move them together. And the reason it wants to do it is because it needs to dead reckon to element number 17, and it can't do that if they didn't move together. Again, that's an implementation detail. Semantically, we don't have to change anything. So the benefits of this is, well, what's wrong with the clicker here? So it's just a collection of objects. There is no special behavior. There's nothing to teach you guys. If you saw the code, you saw the elements, you know how it behaves, right? It acts like any collection. It happens to be fast. Elements of structured arrays are regular objects. I said they can participate, they can be locked. There is no thing you could do to an object that you cannot do to a member of a structured array. That's a key difference from other things like value types and packed objects, which introduce new first-order citizens in the heap that are not objects. A value type is really cool, but it can't be locked and it doesn't have a hash code. That means you cannot pass it to anything that expects to do things to an object, right? Like serialize it, or put it in the hash map. So compatibility is key. We can put things in this bag that are later going into code that doesn't need the bag, that doesn't even know the bag exists, right? We can keep them in the bag while that other code does stuff with it. It's natural. It has one of those effects where once you code it, you just know it's right because it fits. Okay, some more things about structured array. The indices are longs, not ints. Why? Because it would be really silly to limit the index of an array to 31 bits. Right? Nested arrays are supported. They're multidimensional and they're composable. You can have a structured array of a structured array of a structured array. The structured arrays are valid elements in structured arrays. Okay? Non-leaf elements can be structured array, right? But when they are, they have to be of fixed size. So, if you have a structured array of structured arrays, if you look at the top array, all its elements have to be the same size, which means each structured array inside is of the same type and same size, same length. Right? Structured array is subclassable. That was a trick we had to work hard on. It both has to do with what we think is the right idiomatic way to code, because we think there are natural ways to do this. You could look at some of the examples. And that those natural ways will actually enhance what compilers could do for optimization. But the other part is that it's very natural to want to extend an array. The fact that current Java arrays are not subclassable actually stands in the way of a lot of simple things to do. For example, string in Java is implemented as string in a char array. And that gives people pain all the time. It would have been very natural for it to be a subclass of char array. That would be the natural way to describe it. So structured array are subclassable from the start. Now a structured array is not constructible. You have to make it with a factory. Now why is that? Well, this actually has to do more with a limitation of the Java virtual machine spec than anything else. Java does not have a new bytecode with a variable type length. You can new an object that's always the same size. You can new an array that's exactly 6 types. Like, that's all you can do. An array can be a variable length. An object is always of the size of that object because Java doesn't have variable size objects. We're creating a variable size object, or what would be a variable size object if it was optimized. We would need to allocate room in the heap, and there is no way to express that in Java today. If you were to break it down to the order of operations, in Java you first new the object, then you take the pointer reference to what you just knew, and you pass that to the constructor. Our problem is that we need to know how big the thing is, but we don't know how big it is because the constructor is the one that would have to figure it out, and it's too late. Because it's given the object after it was created, and the constructor has parameters that tell how big things are. A factory lets us reverse that. A factory is told what to do, and it internally makes an object and exposes it. It basically gives us the new in construction in one operation. I think it's actually a mishap in the design of the JVM, and hopefully it'll be fixed in some Java version. But until it is, structured arrays are not constructible. They're made with a factory. So structured array.new instance as opposed to new structured array. Now, I don't know how many of you spotted the contradiction I just put on the screen. There's a strong contradiction between the last two examples. I said that structured array is subclassable. I said that structured array cannot be constructed. The problem is that the only way to make something subclassable is to expose a constructor. if you do not expose a constructor, you cannot subclass. The subclass has to be able to call super's constructor. That's just a requirement how the language works. So these two are problematic. Making them both work at the same time was an interesting challenge. And we went back and forth and tried to give up on one or the other and kept saying, no, we need both of these. So if you're interested in some code magic, there's this thing in StructuredArray that I call constructor magic. And what we did here was we said, okay, it has to be subclassable. So there are constructors, but we need to make sure that nobody can ever use them. So rather than make it illegal to write a constructor, what we do is make it impossible to use it. In vanilla Java, there is no way to instantiate a structured array by doing new on it, or in a subclass of it. Now, you can try, and you can code it, and the compiler will let you do it, but you will never get a live object out of it. It will throw an exception in the middle of construction, which means you can never make vanilla code that will actually have one, therefore I'm okay with that, right? It's the second best thing to actually the compiler throwing up on. I wish we could make JavaC throw up on you, but we just make it impossible to work. So that way there are no live examples, right? And there's a really interesting kind of weaving trick on how to make that secure and safe and visible to the user. In fact, when you subclass a structured array, your subclass can have final fields, and you will supply a constructor that will initialize those final fields. You can never call that constructor directly. You code a factory that will call your constructor, and that will work. There won't be an exception if you follow it like that. So there's some interesting trickery in it. Anyway, that was a nice sidetrack. Okay, so far this was semantics. What do optimized implementations of this do? We're running a little long on time. How are we doing as far as people are concerned?
So past 8:30, but
Yeah, a little past 8:30. Just after a long day, I'm going at a slower pace. Yeah. Okay, so in optimized implementation, remember, vanilla doesn't need this. It just works. It's just regular Java code, but when I say regular Java code, the vanilla structured array has an array inside. Regular Java object array that is mutable, but since it's private, only the code we have will mutate it. Okay? The new concept that optimized implementations will have is the notion of contain and container objects in the heap. This is something we believe all JDK implementations that want to optimize the layout will do, and we've studied how to do it in org.JDK and all the collectors, obviously in Zing as well, and C4. And the idea of containing container objects is these are regular objects. They're no different from other objects, but they know whether they are contained, and they know that they are a container. Contain means I'm inside some other object, and container means I have other objects inside of me. It's pretty straightforward. Now, a key capability all the JDKs will need to do is if they reach, or when they're given a contained object, they will need to somehow find the container. The implementation of that can vary quite a bit. For example, you could have each contained object have a header field or a pre-header field that just points backwards or has an offset to where it starts, or chains to it in some way. You can have nothing of that sort and just have nice binary trees that tell you what ranges of memory are containers. There are many ways to implement this. We're not going to get into which specific one, but it's a key need. And the reason you need that is that the garbage collector ever needs to move an object that is contained, it will follow from the contained objects to the outermost live container and move the whole thing together. They need to stay together. They need the offsets to be exactly where they were from day one. That's the only thing we need the garbage collectors to be able to do. There's nothing else special. It's the one operation you need to do, which is why it's fairly simple to implement in pretty much every collector we know of. This is not a hard thing. It's a nice side effect of the fact that we use liveness for regular objects as opposed to have to figure out how to keep a container alive. So there's a bunch of details, and we're actually working on implementations of both vanilla OpenJDK and Zing that will do this. So you're going to see some interesting traffic in the next few weeks, I hope. The streaming benefits of layout come for free on hardware that does prefetching, and that's pretty much all the modern commodity hardware. So if we just make sure that the memory always stays in the same relationship and that the types are of the same size and the stride is there, we don't have to tell the hardware anything, it'll just figure it out. if we walk down 100 megabyte array, one object at a time, and it was laid out that way, we will have perfect hardware prefetching. No compiler tricks, no nothing needed. You just need to make it that way. Dead reckoning is a little harder. So the dead reckoning benefits will probably need some compiler support and at varying levels. The reason is that it's true that we don't dereference. So we no longer have to go to element number 17 by following the pointer to element 17. But this is roughly what the address calculation logic needs to do. So that's the pointer to the element. A is the array. But the array is subclassable, so the body size of the array varies. Depending on how many fields your subclass has, we need to skip through the body before we get to the first element. That's a varies. Then here's the index, but we need to multiply it by the size of the element of this instance. Not all instances of structured array have the same element in them. One instance of a structured array has only one type in it. But another instance of the same class structured array can have another point. I can have a structured array of point, and I can have a structured array of rectangle. Those are two different instances of structured array, same class, that have different element sizes. There's a question there?
You mentioned about moving and the GC having to take care of that. Since these are just plain old Java objects, there's nothing stopping an object being in multiple structured arrays. How is that going to work?
Structured arrays don't have a put operation. And because of it, the only structured array that an object is ever in is the structured array that created the object. And in a hierarchical structured array, that's just a hierarchical thing. So you can have that object participate in other non-structured array collections. You could put it in a list and a hash map, but you can't put it in another object array because there's no put. You can get, but there's nowhere to put. One of the interesting things in this is often the questions and answer. Semantic limitations are really cool that way, right? We're not adding features, we're taking them away. So we're making some questions non-questions. So looking back at this, we have two variables here, the body size and the element size, that are specific to the instance of structured array I'm looking at. Now these are not dereferences, but they're as bad as dereferences. I cannot compute this address until I get both of these things from the array. So how is that different from getting the reference from the array? It's not really that different from the processor point of view. Both of these are data dependents. Right? I need that data to get there. The reason it's more powerful is because, well, these are not constant, but there are two very common optimizations that JVMs do for other reasons and for other things that are usable in structured array in a similar way. How many of you are familiar with class hierarchy analysis? Okay, I'll do a really quick sidetrack there. How tired are you? You want me to fast forward or is it? Okay. Anybody want me to go faster? Anybody want me to go slower? How many of you want the same speed? Okay, I just wanted to verify that you're alive. Okay, so class hierarchy analysis is one of the key optimizations JVM's been doing for probably 17 years. It's what allows you to write getters and setters and not expose fields and get the exact same speed. That's why getters and setters make sense. The way it works is you say, okay, I have this method. This is not the optimization here, it's an optimization this will be like. I have this method, a get, on the color field of the base class animal. I want to get the animal color. It goes and gets it. Now, then I have animal subclasses. I have a cat, and I have a dog, and I have a kangaroo. And each one of them have a color. But they're all implemented the same way. They get the field color. You don't have a separate implementation for each of those. There's one implementation, right? Class hierarchy analysis basically says the JVM can look at all the implementations of a class right now and say, right now, in what I have in the world, there's only one implementer of the method get. I know there are all kinds of class subclasses, and they could have overwritten it, but they didn't. So until this changes, I will know that get means that function, and I'll call it directly, and I don't need to do any of that virtual method stuff. Now, if that ever changes, if somebody loads a class that breaks that assumption, then we throw away the code and we recompile it, re-optimize it, re-jit it. For example, if somebody created an animal called chameleon, and chameleon.getColor depended on the tree branch color the chameleon is sitting on. That's an override. So cats and dogs and kangaroos still use the same method, but this is a different one. It's no longer safe to say there's only one implementer. So we throw away the code, and we can't do class hierarchy analysis-based optimization anymore. That leads us to the second cool thing, which is what's called an inline cache. So since we can no longer prove that there is only one implementer of get in the world, we have to consider the fact that there might be another one. But your dog kennel only has dogs. And when dog kennels get the color of the dog, they never see a chameleon. The optimizer is smart enough to say, I think that's probably what's going to happen. And what the optimizer does is, instead of sitting there and saying, every time I make a get color call, I'll figure out which implementation I should call, which is a double dereferent. It actually says, I think it's a dog. And that's what's called a guarded direct call. I think this is dog, so I will check to see that the type of my object is dog, and if it is, I'll just call the get directly. In fact, because get is really short, I'll inline it there. It's just one instruction. It adds the check instruction. If it is not a dog, then you say, whoa, that's wrong. Let's fix it. Change the code. You optimize it, maybe throw away the inline. But as long as your dog kennel only sees dogs, it'll go really, really fast. Those are the two optimizations that enable that for virtual method calls. They do it by saying, in the hierarchy of what I have, I can prove certain things, or even if I can't prove them, in what I actually see dynamically at that location in the code, I only see that one type. As long as I say, if it's that type, then do stuff, otherwise throw away the code, I can go fast. Both of these can be used for these two things. So for example, yeah, this is structured array get body size, right? But if I can prove that the type of structured array I have does not have subclasses, that body size is a constant. That's like class hierarchy analysis. I don't have to look it up. If I cannot prove it doesn't have subclasses, but I don't think they're going to be called from here, then I can do the inline cache trick and say, if it is this base class, then this is the size. Otherwise, let's throw away the code and figure out what to do. The slow code that will actually have to go look it up will only happen in places that we call megamorphic. It's actual polymorphic calls that actually use multiple types with multiple body sizes. In practice, in idiomatic code, that's fairly rare. In dynamic languages, it's common. But we think in Java, it probably won't be. So that takes care of this one. Now, it similarly takes care of this one because we think that most uses of structured array will not be structured array point, a structured array rectangle, but point array extends structured array point. I should probably have examples in code rather than the brackets in here. We think that it's more natural for people to subclass than to use the generic. And the reason is because the code is much nicer to write, it's much nicer to read when you do that. It's more natural. It also creates a new type that has only a single use, and if you actually use array point or point array, then it's always points. And it's always point array unless you subclass it. So again, you get, the optimizer gets to play more tricks when you do that. So there's a lot of details about this. We did a full workshop talk in the JVM Language Summit a couple months ago that talked about, for people who implement JVMs, which is what that room is for, how you would go about that. I'm not going to get into the details here. So we talked about the first structure. I gave you some examples of what we get for free, what optimization things we need to be, and there are various steps at that levels you could go. Let's look at the other two structure types. Remember, structured array is easy to talk about. In fact, it's the first thing we had, and it's the only thing we had for about a year. But we now have these other two constructs covered as well, and it's actually pretty cool to see how they all play together. So a struct in a struct is what we call an intrinsic object. And we use the word intrinsic in the English language meaning of intrinsic, not in the compiler meaning. Intrinsic means well, you could look it up, I don't remember the definition, but it goes, an object is intrinsic to another object if they were created together and they have some inherent close relationship. That's what we a struct inside another struct is intrinsic to it. So object instance X is intrinsic to object instance Y. That kind of means contained within. Okay? You describe it like that. That's the syntax we're using. There's an annotation at intrinsic, and all the rest of the code is regular Java code, but there's a specific thing, one specific construct you have to use. For example, we're restricting intrinsics to be private and final. We will refuse to intrinsify fields that are not private and final. Okay? There are a couple reasons for this. The final part is stronger than the other. If this is intrinsic, you shouldn't be replacing it and pointing it to some other place. Same as an element in a structured array shouldn't be mutating which element it is. The endpoint 1 should not be able to later point to some other place. That will conflict with the notion that it's intrinsic. Okay. The private thing is more to keep people from doing silly stuff. By keeping it private, we force you to only use that code in this class. It takes away the temptation of people to start using it from other classes and to use a reflection on it too much and stuff like that. You can mess with this a lot. We have to deal with all the ways you can mess with it. So this is how you declare it. That's a regular field declaration. There's nothing special about it, but we're saying it has to be private, it has to be final, or we won't do it. Then this is how you make one. You initialize this by saying construct within. And we're saying construct within this object, the content, and this is the name of the field. And this is the one ugly thing we haven't managed to get rid of in the spelling so far. You have to name your field as a string. This has to match that. You're basically saying, that's a field, I want you to initialize it there. And it'll figure out that this is a point and it's intrinsic from this call. You don't have to spell other things out. It's not very fat. It would have been cool if we could avoid both of these. Right? That's kind of unneeded syntactic sugar. But at least for vanilla implementations, we need to do that. To do better, we're probably going to need language extensions, so who knows, Java 11.
Is it a typo, or is it just supported that the endpoint, the running the string is lowercase p, or is the variable name?
Oh, that's a typo. Thanks for pointing it out. No, there's no convention here. Yeah, it just caught me there. Well, you gotta remember to fix that. Or maybe I should keep it there, see if people notice. Yeah, you're naming the field. It's basically passing that on to reflection. So reflection works the same way. You want to get to a field, you name it. Remember, this is implemented right now in vanilla Java, and it works, right? So, yeah. Intrinsic objects can be laid out, can. They don't have to, but obviously you want to optimize them so it would be possible to do it inside the containing object. So an optimized JDK will know, notice that class line will always have an endpoint in it. It is still a constant size object. It doesn't sometimes have one and sometimes doesn't. So the size of line can be pre-computed at load time to include room for point. It's still constant size. There's no special factory for making line. That's just a regular new. But when you new line, that size will include room for point, and when you initialize line, that's initialization code. That's part of construction. It is valid to do this in your constructor instead of the initializer. You can use either way. Any legitimate way of initializing the final field is valid. It has to use this form. Because it's final, the compiler will force you to only do it once, which is a nice feature for us, right? Doing it twice will be very confusing. Now, this last point is important. We need to deal with and survive the fact that you can mess with this. Using reflection, you can get hold of that field and you can override it. You can make it accessible even though it's private and even though it's final, and you can write in a final field in Java. That's an unfortunate historic artifact of serialization. It actually defeats a lot of compiler optimization. It's kind of sad. Final fields in classes are not final. Only static fields are final. Final fields semantically can be changed without breaking the rules of Java. So we have to deal with that, because it is possible, and it needs to work, and I haven't found a way to make it not work, like with the constructor. Right? So what actually happens is, this reference actually exists. So not only do we have room somewhere in the construct for point, we keep the reference. There's a field called endpoint1, and it points to, it's initialized to whatever this is, so it points to the internal object point. Right? It's there. It's kind of useless, because normally if you go line endpoint1, the compiler will know that that's offset 65 in this thing, and it doesn't need to go through the reference. The whole point is to avoid the double dereference. However, if you ever modify the final field in this class, the JIT compiler will throw away the optimization and start using the reference. That's what it's there for, to survive your potential messing around with the final field. It's a sad, sad thing that we need to deal with that. It's a lot of complicated stuff under the hood, but we can make the semantics actually work. It's not recommended to mess with this, but the only effect will be you will slow down your code. You won't break the semantics, it won't behave differently. Okay.
So does that mean you're incurring that bytes cost of that extra reference on every single string you have?
Absolutely. Remember that part about not saving memory? This is about going fast, and this is going fast.
Okay.
It's there, we never use it, so what?
Okay.
Yeah.
So is this where you have a reference to line, so that then GC time where we did that with the arrays, right? So is the same applicable here? Or?
It's not for GC, it is a reference to line. And the reason we need it is because this code doesn't know that it's being called here. Right? So this factory needs to know what object to look at and what field name to look at to verify that it's private and final, figure out the fact that it has an intrinsic annotation, and dig into the point type and know what type to construct. Notice we said construct within, we didn't say what. It doesn't say point here, because from this and this I can figure out point. That's a reflection magic. And I've been emailing with Brian Getz, and to his credit, he's made us shrink down the syntax to look like this. He wants it to get even smaller. He says, nobody needs that. It's not part of the semantics. Figure out how to spell it better. Right? It's just hard to do that and make it work in vanilla Java. Right? I'm trying to do this without asking Oracle for a single language feature. Because asking for a language feature means changing JavaC, changing the verifier, changing a lot of things I don't want to risk changing. Because I want this in Java 9. Okay, so those are some tricks. Let's do the last construct. Yeah. Yeah. So struct with array at the end is pretty simple. It's a subclassable array. If we can subclass an array, we can effectively describe a struct that has an array at the end. At the end or not doesn't matter. There's a struct and there's an array. Right? There's a variable length per instance thing, and there are fields. That's what an array, subclassable array is. So we capture them with subclassable array classes. Object layout has primitive long array and primitive double array, and they're just subclassable. And they do exactly what you think they do, except that their indices are long. Again, because it's 2014, there's a little bit of a quirk. Is you can actually get a primitive array out of them as long as the index is smaller than 64. It can fit in the 31-bit limitation. There is also reference array as a generic collection, which is subclassable. That's actually very useful. We've had a couple of use cases for it. Now, remember, structured array is also subclassable. So structured array covers the case of a struct with an array of structs at the end, not just array of primitives. That's already covered. So subclassable array gives us there's an array dangling off at the end of a fixed size thing. It's a way to express it. Now, so we talked about these forms. These are the mappings. Structured array does this one. Intrinsic objects does this one. And the various subclassable array forms do the array of structs. The struct with array thing. Now, the three forms are surprisingly composable. This wasn't part of what we thought we would be doing with it. We thought mostly of the use cases in normal C, where you have arrays of structs for all kinds of good uses. But it turns out that because these are objects, you can do some very nice composition. These are actual code snippets from an example, and the example isn't really that much longer. So we have a class octagons, and it just extends structured array of octagon. We think that's the idiomatic way of using structured array usually. Here's how you do a bunch of octagons. What is an octagon? An octagon is an object that has an intrinsic structured array in it. Okay? This is not just a structured array of point, it's intrinsic, and it has a fixed length of 8. So octagon is a fixed size object. It just has room in it for an entire structured array that has 8 cells, each of which is point. That's how you declare that. And then structured array of point is just a structured array of point. It extends it that way. You could take shortcuts. You could make that structured array point instead of that, but we think this is a cleaner code style. And what does this mean? So I have an array, this thing called octagons. It has a bunch of octagon instances. Each octagon instance has internally an array of points. Each point has an x and y. I can take octagons and say I want to go to octagon 57.3x. And I can get to x from the pointer to octagons with no dereferences. This is all math. We get 3-way deep indirection in here with 0 dereferencing. People usually don't do that in C because it's hard to compose in C. This is composable, it's regular object. It's natural. The implementation of one doesn't need to know that the other one even has it inside. They could be separate. You make it intrinsic, you don't make it intrinsic, up to you. And this tends to have some nice things together, right? You could do multi-dimensional stuff, you could index stuff, who knows what you'll do with this, I don't know. I'm looking for examples. Okay, so where are we? We're close to the end, I promise. Vanilla code is up on GitHub. It has tests and they passed. Probably not good enough tests then. It's fairly mature semantically. We're working on the spelling. We're trying to improve and figure out if we could take some other words off. Spelling is like, how do you exactly express something? Arguments over whether it's intrinsic object dot or intrinsic objects dot, things like that. Intrinsified implementations are coming in the next few weeks, actually, to both Zing and OpenJDK. So we're working on this hard. When we have something that's sort of working for OpenJDK, we'll just share the code with the world. We just don't want to put out code when it's not yet working because we want to make the argument about what it needs to be, which is it spelled right? Should it be done rather than how we implement something? The next best steps for this is we want to open an OpenJDK project when we have code that is halfway working, and a JEP to describe it, and later a JSR if it works. And then the aim is to actually add object layout to Java SE. We're hoping for 9, and I know this is very aggressive. I know this is very aggressive. But note one very important thing in the entire design. We have working code today. The only difference is, will it be fast? What we're trying to work out with the exercise is we want to make sure we've captured the right semantics. We want to make sure you can actually spell what you need. We want to make sure it's secure. We want to have at least 2 optimized implementations that successfully intrinsify this thing and make it go fast. Not because we think people should take that code and use it, but because we want to flesh out the API and make sure we didn't capture it wrong. When we know we captured something that is optimizable, we just want it in the spec. And that's the lowest risk thing you could do because we're talking about taking vanilla Java code that works and just moving it into the Java namespace. We don't need OpenJDK to optimize it in Java 9. It would be nice if we get there. But if we don't, we just want the classes in. We can optimize in Java 9.01. It's an implementation decision whether or not to optimize, not a spec decision. So, new Java classes. This will work out of the box on all the Java versions we know of. We're starting with 6. We're kind of arguing whether to move to 7, but we have enough people that are interested in 6, I think. No syntax changes, no new bytecodes, no required JVM behavior. Okay, this just works. We could go fast if people choose to optimize. That's up to the people making the JDKs. Since we're one of the people making the JDKs, we're pretty much sure that they'll be optimized JDKs. And the way things work in that world is if one JDK optimizes it, we kind of push the rest of them to do it too. So we're going to have a Zing support for it real soon, I think, this year. Well, sorry, this next coming year. We're kind of close to that. But Java 9 will be interesting to see what we get. So, thanks. Probably clear the room with a couple of questions.
No, absolutely. While we're doing that, we can kind of multitask. We have a raffle for prizes, great prize. So usually
So you
the
want me
speaker
to do
gets.
this thing? So it's going to be my fault?
Alright, here we go. We've got Decheng? Julie? Decheng? Fantastic. Alright, I'll get your email address. So Decheng's just want a copy of IntelliJ idea. And
Cool.
just, yeah, just he'll give your email details down. And also, just as a thank you for coming to us and presenting, we've also got a gift, a Australian Rules Football.
Thank you.
We really appreciate it. All right, so I'll leave off to questions.
I'll do that and so yeah.
Couple of questions. One is there any good reason to actually start using this in production now without the intrinsification? And the second question was, did Martin concede the argument to you?
Martin is very pragmatic, but I'm not sure he would say he concedes. But the first question, I expect things to change in the API, and we'll know when it's settled. But the answer to that is similar to if you want to use Uni, Oswego, concurrent libraries or not before they're in the Java spec. If they're useful and you think they're good and you want to future-proof the way you code, then you do it. You just are aware that you might need to touch the code, and it won't be very different, but you might need to spell it a little bit. You just need to be aware. I don't want to scare you away from playing with it, because what we really want to do is have people play with it, because we need feedback. We need you to tell us that it's broken and that you can't do the thing you want. Right?
So, just to interject to that, you said about having a JEP and
Yeah.
then presumably a JSR, so then it would be part of the
It would be,
JSR.
but today we have neither, and there's working code on GitHub. I want you to play with it, so please do. Just be aware, right? It'll be in flux. So that's one. As far as Martin, you'd have to ask Martin, to be fair. But Martin has recently said something like, if he had object layout and a C4 collector, and it was everywhere he went, he would probably need to do only half of what he does. Right? And he's lazy. He likes it that way, I think. I gotta find the exact tweet of what he said. Okay.
You said, so contain types can't have subclasses, but if they define their state, what's the reasoning behind that?
So it's not that contain class have to be leaf types. They're not, like, you can take any class and put it in contain. It's just that when you have an array of contain types, all of the members are exactly that type.
Yeah.
You can't have point and a subtype of point in the same array.
So yeah, I understand that. I'm just, the reasoning why, like if the subtype defines no more fields, no more data, the only thing that changes is the B table equivalent. Is there any reason, is there a reason?
Is there a reason for the limitation? So you're right that technically we could have said if the subtype didn't add fields and change the structure, we would still have the layout we want. I mean, it feels wrong to cross that line that way, so I got to think of the example of why it shouldn't happen, but because technically I could still lay it that way. Obviously, if I added a field, I'd break everything. So if the size of it actually shifted, if they're not same size, it wouldn't work. But can you have same size, different type? Maybe. The example I would give you is, if you're just accessing the field, then all you need is the offset. But this is Java. You don't access fields. You access methods that access fields. Those methods need to be inlined to be fast. You want get X on element 17 to be the same implementation, which probably means you don't want a subclass to be able to change which it is. Does that make sense?
Yep.
I think that's the intuitive reason why we shouldn't allow it, even though it can be just size. Right? I need all derivations to be of the type.
And like extensible behaviour would be through other mechanisms. Like
well, you can use, has a versus is a, for that kind of thing. You can have, a structured array of multiple different types. A structured array is not strongly typed on element type. It's just an instance has identical size and type for all elements. You can have another instance that would have, so you can have an array of point, a structured array point, and there could be two implementations. One is structured array point, and the other is structured array subclass of point. Both of them are structured array point generically. Right? You can pass them into the same thing. Just each instance might have a different size, different stripe, different implementation. We think we want to discourage that. Discourage but not disable, right? You can write it. The reason we want that other idiomatic way of doing it, which is I want you to actually say this is structured array point and the point is in the extends rather than in the actual derived class, is because I don't want people to pass multiple types of a structured array into the same call site, because the compiler won't do as well on that site. So I'm trying to make it not the normal way to code if I can help it. But we don't really know what people are going to do with the code, so we'll figure it out as we go.